start working apparently. Okay. So thank you, Prakash. Our next speaker is Gordon Plotkin, and he's going to continue this theme by talking about compositionality, adequacy, and full abstraction from an algebraic point of view.
Yeah, I know physics as I know none. So thank you very much to the organizers for the invitation. And curiously enough, I had been thinking about this anyway, so it fitted in. So here's a little kind of personal odyssey thing in terms of 3 questions. So many years ago, I came across a paper which said that given any semantics, so what's the semantics? You've got a language, some bunch of meanings, and you've just got a function from the language, the bunch of meanings. That's it. Nothing special, just a function. Or a morphism in some category. And it doesn't need to be compositional. Can it be made compositional anyway? Is there a natural canonical compositional semantics you can associate with it? And this paper showed how to produce such a semantics. It's very nice. I couldn't find the reference, so I started reconstructing it. And then I came across this paper by Wilfred Hodges, 2001, and he in fact has the construction of the theorem there. And it's very nice. What you do is, compositionality, as it were, automatically takes care of context. And so his semantics involves a function from context. I think I like that very much, because it's when you do these various examples, like, for example, state there was a kind of a context, or Montague's semantics of natural language, there's always bringing in context. Bringing in enough context, you can make things compositional. So this theorem seemed like a way of doing that. But when you look to see what this canonical semantics was, in fact, it is a canonical fully abstract semantics. Well, because a semantics, what's the difference between semantics with Jamie and operational semantics? The answer is nothing. You just, instead of M for meaning, you write B for behavior. And instead of M for meaning, set of meanings, you write B for the set of behaviors, right? At this level of abstraction, anyhow, there's no difference whatever. And so if you read these as behaviors, then the construction here is the construction of the canonical fully abstract semantics. And that's possibly a nice place for us to go, because, for example, I'll try this with differential equations. You have existence theorems and actually finding solutions. So could there be something similar in computer science? We have general constructions of fully abstract models, but then, of course, in particular cases, to really see it, it's a huge amount of work. But are there cheap theorems? So this is basically all about a single cheap theorem. You're laughing.
Theorems for free, cheap theorems.
Cheap theorems for free. You don't get very much. You don't get very. Cheap theorems are one step up from theorems from free, but not much. Anyhow, it turned out this has all been done before by Schutzenberger. Thank you. Nikolai explained this to me when I came here. Talking to him, we found it. Schutzenberger in 1965 has the syntactic monoid. And later on, that was generalized to arbitrary algebras. I don't know who by, but there's an early reference, Steinbe, 1992. So here the idea is you still have a language like Schutzenberger. L would be the set of all strings. Okay? And you have a coloring. That's just a function from C. It doesn't matter whether it's M, B, or C. To C, a set of colors. So, for example, the colors could be like Booleans, 0 or 1, and you go to 1 if you're in this language, and 0 if you're not. So the question is, can you factor this through a natural algebra, and that is the syntactic monoid. And then you care about the relationship between the nature of the language and the nature of the monoid. That's where the theory. Hi.
I want to make a small objection there.
Good.
Operational semantics necessarily sometimes has to go through a number of small steps, whereas the more abstract semantics does things in big chunks.
Yes.
The trouble with the small steps is you may get errors and other kinds of ways to opt out of something. And it's sometimes very hard to model those in the more abstract way. So I think there are distinctions to be made.
I didn't say there weren't distinctions to make. I'm just saying at this very abstract level.
Too abstract, I thought.
Well, it's only going to be cheap theorems. You won't get much for my money. Anyhow, let's get something. Let's do a quick review of compositionality, which occurs everywhere in language. It's due to Frege, people say. The meaning of a linguistic phrase is determined by the meaning of its parts. So in arithmetic, the meaning of 1 plus 3 plus 5, it's got 2 parts, 1 plus 3 and 5. And you know what their meanings are. Find them out, add them up. You're done. Programming languages, thanks Prakash. So we know that one already. I don't need to go through it again. Logic, the meaning of a conjunction is found from the meaning of its conjuncts. They're both true, false, so the conjunction is false. And natural language, Jack likes Jill, is determined by the meaning of Jack and the meaning of Jill, perhaps. Pardon?
And the meaning of likes.
No. No, this is the point. I didn't say plus, and I didn't say semicolon, and I didn't say and were the parts, and I didn't say likes were a part. So the point here is, what is compositionality? Does a language have a compositional semantics? Is not a fully determined question. It needs a notion of analyzing syntax into parts. And I've chosen one idea there, you chose another idea. And I don't want to choose between the ideas, I just want to point out that's a kind of parameter. And what's more, it may be the case that you should do a syntactic transformation. The meaning of a phrase isn't going to be given by directly, but only via a translation, say, into a deep, say, from surface syntax to a deeper syntax. So there's a lot to just answering the question, does natural language or any other language have a compositional semantics? It really requires a good theory of syntax. And another point I want to make here is that Jack and Jill are objects, and Jack likes Jill as a proposition, and here 0 and 1 are objects. So there can be different types, which is what Prakash always pointed out. But what I'm going to do for the most part, the first part of this talk, I'll do a single sorted thing, and the multi-sorted thing is an immediate, it's just a very simple version of the same thing. I'll just do that in a slide. But so let's just do one sort to keep things simple. You should really have L sub S for S a set of sorts or types or something. Okay, so we need some model of syntax. So what people just take is the initial algebra. You just have an algebraic signature, and you just take all terms over the signature. So we'll take L to, we've got a signature, a collection of binary operation symbols op, each of arity n, and we have the set of closed terms. This is just the kind of thing that Prakash had up there, but slightly more abstract. So if T1 through Tn are terms, so is op of T1 through Tn. Of course, this set will be empty unless you have some operation symbols of arity 0. But you will have those so-called constants. And compositionality at this level just says the meaning of op of T1 to Tn, this op could be likes or plus or whatever, it's just determined by the meaning of T1 through Tn. Another principle, linguistic principle that sometimes people talk about, I don't know if it's the right word, is substitutivity. And this is an equivalent principle. It's sort of saying the same thing slightly differently. If T1, let's define the equivalence relation. T and U are M equivalent if they have the same, if M of T equals M of U. So given any function, you're going to get an equivalence relation, and correspondingly, given any equivalence relation, you'll get a function mapping to the equivalence classes. And I would say if the T's are equivalent, then the ops are equivalent. That's another way of saying it, and that's defined there. Okay. So algebraically, you'll recognize what's going on. We've got congruencies coming up and homomorphisms coming up, but let's kind of spell all that out. So maybe let's go through this slide. So a sigma algebra is a set and maps, a set for the sort, single sort, and maps for each of the operation symbols. Homomorphisms from one to the other just preserve everything. There's initial algebra. The initial algebra is the set of linguistic phrases, according to the previous slide's analysis, what a set of linguistic phrases is. And so that's just L sigma, and the I operation applied to the T's is op applied to the T's. It's just a syntactic thing. And the point is, for any other algebra, there's a unique homomorphism from I to B. It's all known. So H of the ops is the B op of the H's of the T's. So this is all standard stuff. So the question is, compositionality and homomorphism feel like the same thing, but let's just, as it were, spell that out. They're not quite the same thing, but they're almost the same thing. So given a homomorphism, that's a map from I to M. It's certainly compositional because H of the ops is op of the H's. So the meaning of the whole is determined by the meanings of the parts. So that way around is pretty obvious. But what about the other way around? Well, any compositional semantics, here it is here, can actually be factored as a homomorphism followed by an inclusion. The natural algebra to me seems not to be an algebra on M, but an algebra on the image of the semantics. So the set of meanings of L, because you talk about the meaning of the whole determined by the meaning of the part. So we'll take R to be the image of L sigma under M, subset of M, and the operation on the meanings of the parts will be the meaning of the whole. Okay? Now, so that defines operations there. I mean, you could define an algebra in there. So what you would do there, if there were some arguments which weren't the denotations of anything, you just give something arbitrary. That doesn't sound very nice. So
maybe op will not be defined on all of them.
This op is not defined in all of them, only in R. But you could define op in all of them just by making an arbitrary definition if you wanted. But it doesn't seem right somehow. So
you could take partial operations.
Yeah, you can go really, if you want to do partial algebra, that's a well-known jungle. Anyhow, I think this seems to me, he said, since I've got charged, the right way to do it. Okay. Now, we've said well, I didn't say what congruence is, but we all know what congruence is. So given an equivalence relation respecting the operation, it's a congruence. In algebra, when you take the collection of equivalence classes, and the operations work on the equivalence classes in a natural way, and you've got an evident homomorphism. That's something everyone, I suppose, knows. As I said before, substitutivity is just that this relation is a congruence initial algebra. And if you do that, you could use the previous thing and you get another factorization. So this is kind of a dual factorization to the previous one. Instead of looking at a bit of M and doing an algebra on it, we just take L sigma and we divide out by the congruence of having the same meaning. But this factorization is actually equivalent to the previous factorization, some suitable notion of equivalence. But it's just two different points of view. Okay, so that's a quick review of compositionality and substitutivity and so forth. And so what I want to do is begin to work my way towards Wilfred's construction. But in so doing, we can look at what things like adequacy and compositionality mean. I mean, everyone knows what they mean roughly. The point is we can make precise definitions here, and they're even basically categorical definitions if one was to write generally. So I think that's nice. So homomorphic semantics here is adequate for a denotational semantics if this guy determines that guy. In other words, given a sentence here, if I know it's H meaning, then I know it's M meaning. So that tells me there's a function from here to here. So we can simply say that a semantics here is adequate for this given one if this one factors through it. Okay, so that's adequacy. Now, talking about full abstraction, we have to talk about context. So contexts are just terms with a hole in it, one or more holes, and equivalently a term with a single variable x. Either way is fine. Whatever your notion is, given a context, another term, you should be able to plug the term into the context and get the context and determine the context of the context, if you see what I mean. So that gives me a unary function T to C, T and L sigma. And unary functions, these are the unary definable functions in the initial algebra. These will play a major role in what's going on. So generally speaking, given any algebra, we've got the semantics of the context because it's just a composition of functions with a single variable. So that's going to define a unary function. So C sub A is a unary function. It defines these are the definable unary functions. And what's more, for any homomorphism, since it preserves the operations, it's going to preserve the so defined unary functions. H of the C sub A of A is C sub B of H of A. Contextual equivalence is just that two terms are equivalent if in all contexts they have the same meaning. So that's defined relative again to a semantics. And that's a context with several holes. And if you want to do an exercise mentally offline, restricted to context with one hole is equally general. Okay. And so that gives this equivalence relation. And a semantics is fully abstract if and only if having the same meaning is the same as being equivalent in that sense. These are just the traditional definitions in this context. So let's see what kind of a standard fact is that any adequate semantics, adequate homomorphic semantics is at least half fully abstract. This is the easy half, which we always have. You prove adequacy, you get this half. Why is that? Well, suppose T and U have the same meaning. Suppose H of T equals H of U. Then any context, they're going to have the same meaning because that H of C is just C of H there. And then you go, what have I done there? Yeah, I've gone to the U, and that's fine. And you get back out again. That's right. So the C of T and C of U have the same meaning because of homomorphism. Therefore, they have the same meaning according to semantics. So by adequacy, that's the case. So that proves that way around. It's the other way around that's more hard. Is that okay? Yes. Okay. But can we say this diagrammatically? So we're interested in the meaning of something in a context. So that's saying we're interested in the meaning of something in the function space from context to meanings. Okay? So we've got a meaning M sub context. We can lift the meaning function from L to M to a function from L to M context by the meaning of T in a context is the meaning of T at a context is the meaning of T in the context. Okay? And we could do something similarly here. And then there's this natural function here. What does it do? It takes A, and in the context, you take something you apply the definable function, unary function that this context defines, and then do the original little m here. So this diagram commutes, and to say that is to say the previous lemma, but more categorically. And using this, so any adequate, so to construct this diagram, you have to have an adequate semantics. And using this diagram, you can say what full abstraction is. Full abstraction says if two things are the same in all contexts, that's to say if they receive the same value here, then they receive the same value there. Okay. In particular, if this happens to be a mono, then that's true. And conversely, if this is a surjection, then this is a mono if it's fully abstract. So this is a notion. So say this is a mono. There's a notion of semantical full abstraction, which I found in Sampson's papers at some point. So that's a categorical definition of semantical full abstraction. So now we have categorical. I mean, I'm only writing in sets, but we have categorical ideas now for adequacy, full abstraction, semantical full abstraction. They're all quite natural in terms of various diagrams. Jolly good. But there's one thing we haven't done algebraically. We've got this equivalence relation of being equal in all contexts, but that doesn't sound algebraic. But in fact, there's a very natural notion of this. It turns out that two terms are equivalent. This congruence is simply the largest possible congruence that you have on L sigma, which is compatible with being equivalent, semantically equivalent. So why is that the case? Evidently, if you're equal in all contexts, you're equal in the empty context, so you're certainly a subset of there. And suppose we've got two terms which are equivalent. Take any context. And so what's the meaning of C of op of T of U? Well, we've got, as it were, the context. I don't know. Suppose you make a hole just here. Okay, then U and U prime have the same meaning in all contexts. So these two things have the same meaning. Now we'll keep this U prime fixed to make a hole just here, and then you get the other part. Okay? And so notice that this argument critically depends on the function symbols being finitary. It'll break down if they're infinitary, and we'll see a counter example later because of that. And the largest is another little argument, which I think I'm going to skip because I can feel time slipping away. Okay. So now that's actually enough preliminaries to give Wilfred Hodges' construction in one slide. So what we do is we just take our language and we divide it out by this largest congruence. Okay, so that's the definition here. We get this thing commuting, and so that says what we've got is an adequate model, and then we can construct this thing, but then it's easy to see that this makes it fully abstract. Because suppose two things have the same meaning here, that means in all contexts they have the same meaning. That means that they're congruent. Well, that means they have the same meaning there because they go to the same equivalence class. And this is a surjection, so it's also semantically fully abstract. So that's as cheap as you can get, Dana. But it's very pretty all the same. So there's absolutely no information about what this could possibly look like, but it exists. Okay, so that's pretty cool. It exists in this simple situation. It's actually got nothing to do with whether the fact that this is the initial algebra. The same construction works for any algebra. So you can take any algebra and any semantics or coloring. You have the equivalence relation as before. In any context, we can say two things are equivalent if they're equivalent under the application of all unary definable functions. And once again, this becomes largest congruence, and we have a generalized notion of full abstraction. Okay. Now, this might be useful. Suppose, for example, we want to build in some equivalence relations into our programming language by having some algebraic theory. Like, for example, to continue Prakash's example, semicolon is actually associative, and skip is the identity. So we might not want to take the theory of a monoid. So it turns out that whatever equations this obeys, this obeys too. So here you get a full abstraction for languages with built-in, or I forgot what it's called, but yeah, the similar things happen in process algebra theory. So you still get full abstraction there. And so in general, given any finitary monad, a finitary monad is something you can just axiomatize by function symbols of finite arity. You get a fully abstract semantics for any free algebra there. So in the case when this is monoids, that sigma is the alphabet, and this is the Schutzenberger construction. Okay, so everything fits together. That's nice. I said in this case, the one-hole contexts have the form familiar from the syntactic monoid definition. Good. So feeling happy momentarily. I want to do some other examples. So I said that you can do multi-sorted, so we're going to do that in one slide. I'm assuming you have 10 minutes or something.
No, actually,
15? Okay, let me try for 10 then. And fail. Okay, so anyway, so here we have a signatures, a set of sorts, operations. Now, the arguments are sorted and the result is sorted. So we go from S1 to SK to S bar. So for example, likes goes from two objects to a proposition in the natural language case. Algebras, you have carriers for every sort, and operation symbols are suitable functions on the product of the carriers. Congruency is suitable families, equivalence relations. Colorings now come in families. It might be the case, suppose you're doing operational semantics, that you only care about a particular category in your programming language, like arithmetic expressions, and the coloring is the value that they evaluate to. But you're still required to have colorings for all the other things, but you can just take trivial colorings. That take CES to be a one-point set, and that does it. So congruence for syntactic algebra is so two elements at a sort are, why is that seat there? I've totally forgotten. Anyway, they're equivalent. I can't see why. Anyway, they're equivalent at S if for every place S prime you can map them to in every context, it goes from S to S prime. Oh, that's the coloring, sorry, yes, it should be capital. Then CA at A is equivalent to S prime to CA of A. So two things are congruent if whenever you map them to anywhere, they have the same color. Okay, and then you get exactly the same diagrams and theorems as before, but it's not worthwhile writing it all out. So that's good. So let's do something prima facie a little more challenging. Well, I should say in parentheses, I'm not going to do anything domain theoretic, but what one can do it, but it just seemed like you're getting into technicalities about topology and so forth that won't benefit the discussion. So but I thought I'd at least do this example because it's nice. So we've got lambda calculus, and that has a binder, so you have free variables and it's bound by a lambda, so x is bound in M. Or we have integration, this dx is a binder and it binds this x in the function symbol, but there's nothing but A and B are not bound by it. Quantifiers for all x, phi x, this x binds phi. So these things occur all over the place, right? Can we deal with them as well? So the idea is you have a fancier notion of signature. So what you do is a binding signature, an operation no longer is this is unary sorted, but with binding. Okay. There's also multi-sorted with binding, but never mind. So each argument of the operation can now bind some variables. So there's k arguments, and the ith argument binds bi many variables. Okay. So for example, lambda calculus app is 0, 0, because it's got two arguments and doesn't bind any variables in either. Lambda is 1, because it's got one argument and binds in that argument. Integration is 0, 0, 1, because it has three arguments, doesn't bind those, and it does bind this one. Okay. Generalized quantifiers, all these things fit into this kind of picture. So we have binding terms, and given a sequence of variables, we can say whether or not a term M is a valid term with free variables x1 through xn. I haven't spelt out the details. I should have a formal system of the kind that Prakash referred to, but I'll give one nasty example, because this is, as it were, the different thing. So here's a binding term op that's going to have k arguments, and the first argument will have b1 many parameters, and the kth argument will have bk many parameters. So you write all this. So is this a valid term with these free variables? Well, you take a particular m, and you have to say that it's a valid one given the free variables x1 through xn and these additional variables. You may say in the back of your heads, what happens if there's a variable collision? And there's bits of random magic you're supposed to discuss in detail which say, don't worry about it. So don't worry. Just pretend there can't possibly be. Okay. Okay. So what's the notion of a binding algebra here? It turns out to be a well-known notion. Well, a reasonable thing to do is the notion of a clone. An abstract clone rather than a concrete clone. So it's not a clone of operations, it's an abstract clone. So you have a family of sets, Cn. These are going to be the meaning of the terms with n free variables. And you have projections and a composition given as it were, a function. Think of it as a function, an abstract function with n arguments and n functions with m arguments. You get an emery function. so you some axioms for projection. So you can do composition. Sorry, that is a composition. But rather than actually write comp a lot of times, I just write f. I write f of g1 through gn rather than writing comp bracket f comma g1 through gn and so forth. So we have a bunch of obvious axioms. So those of you who know will know perfectly well. This is a one-sorted multi-category, and it's also a pre-sheaf in a suitable category. But I'm just going to take this concrete thing to work with. Operations, but I guess the novel point is not only that you have a clone, but that you use the clone to interpret your operations. Okay, so these are the operations. So what are we going to? Suppose I've got. See, the clone eventually is going to have. Let me see. Yeah, let me go back to here. See, we're going to have to interpret this, but given an operation, it might have. I should really put a p here. It can have all these x's free in it as well. So we think of these as parameters. So we need an interpretation no matter what our collection of parameters is. So we need a family of meanings. So suppose we've got p parameters, then the result of it will be a function, as it were, with p arguments. And say at the first thing you're going to bind b1 things. So the first thing is going to need a b1 plus p parameters and so forth. So you're going to have a family of p's of opt parameterized by p of this nature, and you want these all to be connected. So you want, roughly speaking, if I compose with these parameters, compose some functions and then do the op, that's same thing as doing the op and then doing the composing. This is called the uniformity condition, and that's here. And that, again, comes out naturally if you do some pre-sheafy version of this. The semantics is given any m with prescribed ordering of its free variables, then you get an element of Cn, or just write Cm, you don't bother with the details. And this is an example here. You're basically saying C of the ops is op of the Cs. Okay, so this is compositional, but it's the right notion of compositional for this rather nastier form of algebra. You can define homomorphisms, and they're just exactly what you think, a family of maps from Cn to Dn which preserve everything in sight. And congruencies, they're equivalence relations which agree with everything in sight. And yes, yeah, so what I want to point out, if we go back even to the beginning, to where here, it looked like we were doing something different, but in fact we've already done this. This is a particular case of a multi-sorted algebra, right? So we could apply the theory we already have, and so we automatically have full abstraction. So that was kind of cute. But that, as it were, isn't very explicit, because you've got all these free variables on the one hand. On the other hand, you've got all these numbers n, and it's very annoying. You have to translate backwards and forwards. So I want to show you a little bit of the translation and how it comes out after the translation. Okay. So let's see. So this is a particularly nasty one. So how do I describe the initial algebra in terms of terms and variables? Well, I wanted to say what's in CK, Cn here, at every n. So it has to be terms with n free variables. But which free variables? So you just do some standard free variables z1 through zn. Now we're always going to work with terms with free variables z1 through zn, and that means we're constantly going to have to be renaming all these variables. And maybe I won't, and one suffers, let's put it that way, but it's perfectly fine. And it's very annoying when one has to do this suffering. And anyway, this kind of suffering occurs in many places in category theory and algebra. Okay, how about full abstraction? Well, I don't need to say any more because I've already said what it is, but it'd be nice to translate what I did say into this kind of termy thing. And so one can do that. Yeah, I'm going to use that 5 minutes. So let's say contexts are terms with a whole. Like here's one. And this whole binds what y has binding force in it, and x is binding force in it. So this context will capture any x's and y's. Okay, so we talk about when a context captures some things, and the contextual equivalence is as follows. M and n are equivalent if for any you take any sequence of variables y1 through yn, and you take any context capturing y1 through yn. You take this m is going to have three variables x1 through xm. So you take m, and for x1 you substitute p1 and all the way through, and then you get a term whose free variables are exactly y1 through yn. This context is then going to capture it, and so this will be a closed term. So I'm assuming only that we have a meaning for the closed terms. So say m is equivalent to n if that's equivalent to that. And fully abstract model, which is just another way of writing, though you have to do some work actually, is that there's a binding algebra C such that two things are equal if and only if they're equivalent. So that's another cheap theorem, but slightly less cheap than the previous one. Okay, I thought it might amuse you to look at. So a question is, if we do universal algebra before, what's universal algebra here? And so here's some equations for logic and for lambda calculus. So for example, eta says if I apply x to y and bind in y, that's the same as x. This is the untyped lambda calculus. What's beta? Well, if I take lambda x and apply f to x, then that's f of x. But it turns out this f, to be axiomatizing properly, is not a variable. It's a function variable. You have to allow function variables to get a proper equational thing. Okay, and equally here, you see where it's gone to. I'm talking about for all f of x. I need to be able to substitute in for this some abstraction to get general formulae. That's what goes on. So that's kind of cute. I mean, it's interesting to do this in Berkeley, which is one of the places where algebraic logic got invented. So here's another version of algebraic logic. Okay, logic is just some algebra with quantifiers, with binding symbols, and to algebraize it, you give an equational theory. And it's pretty easy. I won't go through details. These are the right equations for all to present the rules of first order logic in this way. And if you want a fun exercise to go home with, this is nothing. It's just ordinary first order logic. For any sentence find C, set phi equivalent to C if phi is provable if and only if C is provable. And then show that that should be var phi. Two things are equivalent in a sense if and only if they're provably equal.
Context level for first order logic.
Is it?
Yeah, you prove the context level. You're saying that context reduced to universal binding.
Yes. Oh, this is well known.
No, I'm just saying it's a version of a context level for first order logic.
Yes.
Semantics
Yes.
is compositional.
It is. Yes. Yes. That's true. So what? That's not the point here. The point here is that this equivalence relation of interprovability is given this way. It's a little theorem to prove. Okay. So having everything being positive, I want to almost conclude with something negative. So here's a little theorem. Let A be an algebra with two congruencies, such that the least equivalence relation containing them is not a congruence. Any algebra axiomatized by finitary operations that the hypothesis cannot hold.
Sorry, but what is a congruence?
What's a congruence?
I mean, is it the equivalence relation or?
The equivalence relation preserved by the operations,
Right.
whatever they are, and whatever your notion of equivalence relation is, whatever your notion of operation is. Okay. Then A has got no syntactic algebra with respect to the coloring corresponding to that, and it's an easy proof. And I'm not going to take the. Basically, you end up showing that this equivalence relation, this congruence, has to actually be this, but this can't be. That contradicts the fact that this isn't a congruence. But I think I'll skip the proof. And then Nikolai has this nice counterexample. So the idea is think of some sequence A0, A1, A1, A2, A2, A3. Then the one congruence is going to make A0 and A1 congruent, and A2 and A3, and then A4 and A5, and so forth. The other congruence is going to make A1 and A2 congruent, and A3 and A4, and so forth. So between the lot of them, everything's going to be congruent to A0. But if you start off with it, but the number of steps that you need to take to get to A0 keeps increasing. So this thing, although you can get any individual argument down all the way, you can't in finitely many steps get all the way down. And it's only finitely many steps we have available because of the fact that we've got an equivalence relation that just lets you do one step. So these are two things which are not equivalent, but they are congruent. So that's pretty bad. Okay, so that monad is not finitary. So a conjecture question, which we don't have an answer to, is say that a monad T admits syntactic algebras if any T algebra is syntactic algebra with respect to any coloring. Conjecture is T admits syntactic algebras if and only if it's finitary. I don't know if that's true or not. Nikolai has some a particular case of that, if T is of a certain nature, then basically being of that nature means you can transpose that counterexample to that context. So you get a bit more general, but we don't really know. So we're relying on you to solve this one. Or someone. Someone who's more intelligent than both of us. So. Okay, what next? Well, this seems quite nice. So there's lots of natural questions that come up. So things work well for finitary monads. So how about enriched finitary monads? So is it the case that if any monad enriched over a locally finitely presentable category admits syntactic algebras? I think it is. That should be okay. A question of suffering through definitions, but I don't actually know. It's nice that we can do things at a general level. We seem to have done, even if only cheaply, full abstraction and so forth, and adequacy at a general level. What else can we do at a general level? And can we relate things? In particular, I think an interesting question, this is a connection, but are there useful connections on one side or another between semantics of programming language and algebraic language theory? For example, duality is very important in both, and that is not a coincidence. I think there's a similar things happening there, but they're being used for different purposes. So I think that should be investigated. And then, of course, going back to Prakashian physics, what happens beyond the Cartesian case? So thanks a lot.
So about the binding algebras with the lambda signature, this would correspond, so if you have not stated, but I assume that adequacy and perhaps even full abstraction results are formulated in the same way.
Identical, these are particular examples.
This would correspond to what we, from a model theoretic perspective, what we used to call lambda algebras. And then there's something called lambda models where you also have extensionality, which is not an algebraic identity. It's first order. And the question is, I do believe that for single models for which full abstraction was shown, they were actually lambda models.
Yeah, that's a good point. I mean, one needs to go back and relate that to these previous frameworks. I haven't done that.
Right. So I mean, just
I presume what you're saying is
with respect to lambda is what's usually called weak extensionality, but strong extensionality is more interesting because that's what happens in the models of.
Yeah, I'm sure what you're saying is right now. It'd be good to double check. Yeah.
Yes, Dave.
There's another pitfall, and I wonder how it fits into your schemes here. Take primitive recursive functions. Everyone agrees that if you have a given function and make a primitive recursive definition, then the resulting thing is fully defined. But equations between primitive recursive functions are not recursively enumerable. So no proof system ever gives you all true equalities between primitive recursive functions as whole there.
Right.
So isn't that a pitfall here in thinking about, the primitive recursive functions compose like crazy and everything is very nice, but knowing which equations are true is difficult.
Yes. Yes, I mean, we know the fully abstract thing exists, but it can be absolutely horrible. Yeah. In this particular case, it would be. There's no reason why it has to be RE or anything.
Other comments or questions?
I'm still trying to connect these two talks. So,
That's your problem. I mean, we just have to give them.
so the notion that seems to be the connection is this notion of independence. So if you've got physically independent systems, you can reason about them separately and then compose them.
Yes.
And it looks like the notion of context is where you have some interaction, and that's a way of basically making explicit what the interaction is. And if you take context into account, you can still get a degree of compositionality.
Yes, it's saying that you can get it cheaply because if you just take all possible context into account, then you're compositional in that. But what you would like is some limited notion of context.
Yes.
Yes. So in particular, instead of you could take the semantics to be the set of formulae that are true of the system. And then that won't be compositional in general. For example, in process calculus, it isn't. And this will give you, says, well, there exists some way of making it compositional. But who knows what it is, apart from these generalities. Yeah.
Samson has another.
Just a sort of comment on the relation between the talks. I mean, Prakash was emphasizing the connection between operational semantics and denotational semantics. And here in the world you're talking about, you're not referring outside the given semantics.
Oh, I am. I am. Because the operational semantics is just a semantics. And the homomorphism is a denotational.
Yes, okay, but you're not, right, but it's cheap in the sense that you're not sort of looking at a detailed, you're not getting a detailed picture.
No, again, absolutely no information, just existence results. But it should cheer up those people climbing the mountain to know that there's a top. Yes. So any particular example has problems. You get something, but
Right, well,